Okay, I think we know enough now to use some of this data to determine the structure of an unknown, and then we'll be doing some more of this a little bit later. You're given the spectrum. They've given you the integration data. They've also, from mass spec, from mass spectrometry, they've been able to give you the idea of what the molecular formula is. They also ran an IR and found carbonyl absorbing at 1700. So we know there's a carbonyl. We know there's 4 carbons. All right, so we know we've got one of the 4 carbons is this guy. Also, one good thing to check is to see if there's any double bonds or triple bonds. So the chemical formula C4H8. Okay, if this was an alkyne, or sorry, if this was an alkene, if it was saturated, in other words, it would be C4H10. So what this is telling me is we have only 1 degree of unsaturation, and that's present here in this carbonyl. So there's no other double bonds or triple bonds or rings. Okay. So H8, we've got 8 protons to deal with. If we look at the integration data, 15 plus 11 plus 14, this becomes 40, and there's 8 hydrogens. So that's 5 units of on our amplitude here per hydrogen. So that means 15 is equal to 3, 5 is equal to 2, 4 is also equal to 3. And that gets our 8 hydrogens. Alright, so C is going to be equal to 3 hydrogens. B is going to be equal to 2 hydrogens. A is going to be equal to 3 hydrogens. So we have 1 carbon accounted for in the carbonyl. We have 3 others to deal with, and they each have hydrogen. So this 2 hydrogens here, this has to be like, right, this is CH2, this is a CH3, and this is likewise a CH3. 3 hydrogens. From the splitting pattern, we can tell what their neighbors are. Okay? These 3 hydrogens are split into a triplet, okay? Which means they have to be next to, if you want to think, well, it's an n+1 rule, but you might want to think of it going the other way around. It's the n-1 rule. So 3 minus 1 gives me what? 2 hydrogens. The protons responsible for this signal are next to these 2 hydrogens. Not these ones, because there's 3 here, so these 2. So this is that kind of classic example of a triplet quartet. If you look at these 2 hydrogens, they are split into a quartet. Again, if you want to do the n-1 rule in this case, 4 minus 1 is 3. These guys have to be next to these. And if you want to get really picky, you could look at the J coupling here would be the same as these guys. So we know that they're coupled, that they're actually splitting each other. Okay, so we have, from these 2, we have a CH2, CH3. This carbon, no, okay, this carbon is at the end of a chain, so it's only got 1 neighbor. But this one is got to be another bond here, right? What is this going to be bonded to? Well, it can't be bonded to anything with a hydrogen, because if it was, it wouldn't be split into a quartet. It would be that more complicated splitting pattern that we looked at, where we had first split into a quartet from these, and then if there's at least 1 other hydrogen here, it would be split into a doublet. So we'd have a quartet of doublets, or 8 peaks, but we don't see that. We only see these 4. So we know this has to be attached to this carbonyl. So it's going to be CH2, CH3, by processes of elimination, that means these guys have to be this CH3. And now if we also look at the chemical shifts, this makes perfect sense. These two peaks that are next to the carbonyl are shifted down. The one that is furthest from the carbonyl is upfield. And so what we have, whoops, I take that back, we're missing an oxygen. That would explain why this is so far downfield. Okay. So we have an oxygen, so there's two possibilities here. CH3 right, we could have methyl propanoate or propionate, or we could have ethyl acetate. The way we're going to be able to distinguish between these two possibilities, and you can see why I've written these two possibilities down, they correspond to the splitting pattern, right, that we talked about here. This three hydrogens give us a singlet, okay? But what we need to know is this carbon bonded to the oxygen here, or is it bonded to the carbonyl? When you have a hydrogen on a carbon that's bonded to a carbonyl, as this would be, okay, 1.5 to 2.5. If it is bonded to a carbon that's directly attached to an electronegative atom, such as nitrogen or oxygen in this case, right, it's shifted further downfield. So the one that's bonded directly to the oxygen is going to have a signal further downfield. See, that's these three hydrogens here. They're bonded directly to an oxygen, so they're further downfield. If it was this one, this CH2 here, for this signal B, would be downfield more. So this one is bonded to the carbonyl, shifting it downfield in the 1.5 to 2.5 range. I can write that down. When we have bonded to a carbonyl, we have the 1.5 to 2.5. When we have hydrogen directly bonded to an electronegative element like oxygen or nitrogen, then it's shifted further downfield, 2.5 to 4. That tells us we have this guy. Okay. This is 1, 2, 3 carbons would be propane. This is a propionate. This is methyl propionate.